Today we're going to continue on with section 3. Yesterday I cut the lesson in half because of technical issues and the fact you couldn't hear me. So what we're going to do is we're going to cover the rest that I did not get to cover yesterday. Okay. So symbols and formulas. What do chemists use to represent elements and compounds? Now we talked about elements yesterday and we talked about compounds. So as a reminder, let's kind of go over this. Remember, elements are made up of one kind of atom, and it cannot be broken down. Compounds, on the other hand, are made up of two or more different atoms or elements, you could say, and they can be broken down. And remember, they can be broken down chemically, so only through chemical means. So let's go on to how we represent these two things that we talked about last time. Well, what we do is we use symbols to represent elements, symbols, and formulas to represent compounds. So some symbols you might have seen are C, H, O, Ca, Na. You've probably seen these in junior high. Hopefully you recognize C as carbon, H is hydrogen, O is oxygen. And these ones over here you may or may not recognize them, but Ca is calcium and Na is sodium. Formulas are where you take these symbols and you combine them. So formulas are like the one we saw for sugar, C12H22O11. So you see how we combine these three symbols to make a formula. Even H2O, I've taken oxygen and hydrogen and combined it to make a formula. So using symbols isn't actually a new idea. For thousands of years, we have used symbols such as, like, for example, this little doodly thing for lead, tin, and zinc. Even famous scientists like John Dalton, and we're going to talk about him later on, he used drawings to represent different elements. Thankfully, we don't have to memorize all those drawings because a guy named John Jacob Berzelius, I can't pronounce that, came along and he decided he was going to give elements symbols, or in other words, letters, based on their Latin names. So each element symbol is a 1 to 2 letters. So some of them can be one letter, like carbon and hydrogen and oxygen, like we saw before. And some of them are 2 letters, like calcium. Notice that the first letter is capitalized, so it's a big C. And the second letter is always going to be lowercase or a lowercase a. This is the correct way to write a symbol. And I want you to write them the correct way. If you don't, it would be incorrect. So make sure you guys understand how to write them. Okay. Now, the weird thing about Latin is a lot of languages are based on Latin. They have Latin roots. So a lot of times the English name and the Latin name of elements are similar. And so when we see these symbols for these elements, we think that they're named after the English name. So we think, for example, Ca for calcium, N for nitrogen, and S for sulfur. However, that's not always the case. Since they're named after Latin, some Latin names are different than their English names. For example, sodium becomes natrium. That's why sodium is not S or SO. Sodium is Na because of the Latin name. Potassium, most people think potassium is P, but that's in fact phosphorus. It actually gets K because of the Latin name kalium. Now you're going to be using this diagram on your homework. So on your homework, when it asks you to refer to this, this is actually the little data table you're going to refer to. Another example is tin. Most people was like, why is tin SN? And again, based on the Latin name stannum. So chemical symbols provide a shorthand way to write formulas because what they do, like I explained in the beginning, is they take these symbols and combine them. So they took the H and the O to make H2O. They combined the carbon, hydrogen, and oxygen together to make sucrose or table sugar. The only thing that's a little bit different is that the chemical formulas have something known as subscripts. So if you don't know what a subscript is, it's those tiny numbers that come after the letters. If there's a number that comes after the letter, it tells you how many atoms there are for that element. So for example, there are 2 hydrogen, and if there is no number, it's an understood 1. So there's 1 oxygen. And again, this is fixed and it's always going to be the same. Again, we've been using sugar as an example, C12H22O11. This means there's 12 carbon, 22 hydrogen, and 11 oxygen. So chemical symbols are abbreviations for the names of elements in what language? So I want you to see how you answer that. And the last part of this chapter rounds out on the periodic table, and that's because all known elements are organized on this periodic table. Every element that we know about is up there. Even if we haven't quite named it yet, you're going to see it. So some elements we haven't named yet are the ones that are going to have 3 letters. They're just temporarily up there to hold their place. So what is the periodic table? Well, a periodic table is an arrangement of elements in which the elements are separated into groups based on a set of repeating properties. So I would accept it's an arrangement of elements based on properties. That is an awesome definition. So the arrangement of elements based on properties. So why is it actually useful? Since the periodic table is actually based on properties, it allows you to compare the properties of elements to one another. So for example, I can look at calcium, and since it's in a certain group, know it has certain properties. And then I can compare it to like chlorine. Now, I will go more in depth on the periodic table when we reach chapter 6. It's actually the last chapter that we cover of this semester. So when we get to that chapter, we're going to learn more about how the periodic table is arranged. But for right now, this is a general idea of what it looks like. I have a periodic table in the front of my classroom, but also on one on my website under helpful links and resources. Each element is going to be identified by symbols placed in the square. So for example, hydrogen gets the symbol H. We've talked about calcium gets the symbol Ca. Even carbon gets the symbol C. Now, they're arranged like this every time because they need to be in that way in a specific way. Elements are also listed in order from left to right and top to bottom by atomic number, and that number is unique. If hopefully you remember from integrated science, the atomic number is the number of protons in an atom. So if we actually go back, it says the atomic number of the element is shown centered above the symbol. So in this one, if you look above the symbol, you can see a 1. So hydrogen has the atomic number 1. And then it goes in order. 2, 3, 4, 5, 6, 7, 8. And there's no number that is repeated. They each have their own number. So hydrogen is the lightest element. It's in the top left corner. Helium, again, gets 2. Then if you were to go back, lithium gets 3. And as you read it left to right, it's going to keep increasing by 1. Now a touch up on what rows and columns are called. So a row is called a period. So they go left to right, so side to side. There are actually 7 periods on the periodic table. So some periods are only going to have a few elements, like period 1 only has 2. Or you can have a bunch of elements, like on period 6 has 32. So let's take a look at that. So here's your first period, second, third, fourth, fifth, sixth, and seventh. So you read it across. See how the first one only has 2 elements, whereas the second one actually has 1, 2, 3, 4, 5, 6, 7, 8, and so on. So within a period, the properties of the elements vary. So if you go across the period, they're all going to be different. So they're going to be different properties. However, when you go down to the next period, so you start over again, you're going to see that those properties are going to repeat. They're going to be different across, but for example, everything at the beginning is going to have the same property. Everything right here, these 2 are going to have the same property. These 2 are going to have the same property. So it repeats. And that is where we get groups, or we call them families. These are vertical columns. They go up and down. These are ones, because you have repetition as you start a new period, we get where groups, if you go down a group, they all have similar chemical and physical properties. So for example, if we have group 2A, this contains beryllium, magnesium, calcium, strontium, barium, and radium. And then we're going to take a look at that real quick. So for example, here is our groups. So this is a group. 1A, 2A, 3A, 4A, 5A, 6A. And then you can look down the group. So beryllium, magnesium, calcium, strontium, barium, and radium that we were talking about, these are all going to have the same chemical and physical properties. And we'll get more detail in that when we cover it in Chapter 6. Again, this is just an introduction. Okay, so that's the end of 2.3, so Section 3. Let me know if you have any questions. Oops. I'm going to get this just